This program is brought to you by Stanford University. Please visit us at stanford.edu.
I wanted to do a little more with the idea of a particle in an electromagnetic field. I wanted to work out in more detail the theory of a particle in an electromagnetic field, a charged particle. We're not going to worry in this course about the dynamics of the field itself. Of course, the dynamics of the field itself, the field is a dynamical system. It itself has equations of motion. You can follow them. For our purposes now, the electric and magnetic fields are simply given to us. And in fact, to make things simple, let's suppose that the electric and magnetic fields don't depend on time, although they may depend on space. I've worked out for you the theory of a charged particle moving in a magnetic field. I thought we would redo that, talk about it a little bit, because it is unintuitive. Some things about it are unintuitive. In particular, the canonical formulation of it, the Hamiltonian formulation, the notion of momenta is a little bit surprising. And there are some unintuitive things about the way a particle moves in a magnetic field, in particular when you add an electric field. So it's called the Hall effect for those who wonder, who may know what I'm talking about. All right, so let's begin. We have various, in fact, we have various different formulations of mechanics that we've done up till now. Let's just list them. List the various forms. We're going to learn one new form, but the first form is just equations of motion. F equals ma. All right. Let's call it equations of motion, and those are typically differential equations which come down from above. Newton or somebody tells us what those equations of motion are, and they're of the form of second-order differential equations for the coordinates of a system. Next was the principle of least action. Not any equation that we can write down will be of the form that it can be derived from a principle of least action. But all the fundamental equations of physics are derivable from a principle of least action, including, incidentally, the field equations governing the electromagnetic field, but we haven't gotten to that yet. Least action. From the principle of least action, we can derive another form, namely the Lagrange equations of motion, the Lagrangian form. Those are derived by applying the method of the calculus of variations to the principle of least action, in other words, the Euler-Lagrange equations, and that gives us the Lagrangian form. And then finally, by concentrating on phase space, the p's and the q's, we ultimately wound up with the Hamiltonian form. They each have their advantages and disadvantages. The Hamiltonian form is perhaps the least intuitive. On the other hand, it has the most to do, first of all, with quantum mechanics, but second of all, with information flow. It has this lovely picture of a flow of points through phase space, which if you follow them, you not only see how a single system behaves, you see how the whole ensemble of systems with different initial conditions will behave, and allows you to compare them. It allows you to discuss, for example, information conservation and other things that we'll come to. So that's the advantage of the Hamiltonian form. The disadvantage is in some ways it's less intuitive. In particular, we'll see that tonight when we talk about the electromagnetic particle. Lagrangian form, very, very general, very, very powerful. I can't think of very many disadvantages of it. It's powerful, except that it doesn't do some of the nice things that the Hamiltonian form does, namely allow you to plot a flow through the phase space. The principle of least action, that underlies everything, extremely deep. But in its form, in the form in which you write it down, it is not terribly useful. The way you use it is to derive equations of motion from it, namely go to the Lagrangian form. So the principle of least action underlies the whole shebang, but by itself, it doesn't tell you how to solve problems so easily. Minimize the action. Usually you do that by solving a differential equation. And equations of motion, well, those of course are the lowest common denominator in the sense that all systems have equations of motion. We learn about them in elementary physics, F equals ma. But just knowing that there are equations of motion, differential equations, is not sufficient to tell you about energy, momentum, and all the special things that go with the special form of the equations that physics makes use of. So they're all interesting and all useful. We can apply each of these to the motion of a particle in an electromagnetic field. Now for tonight, I'm mostly going to be interested in a particle moving in an electromagnetic field in 2 dimensions, just because it's easy to visualize. In other words, a particle free to move around on the blackboard in an electromagnetic field where, for simplicity, the magnetic field will be into the board, no components along the surface of the board, and the electric field will be parallel to the board. We'll come to that. But before we do, let me write down the general equation of motion for a non-relativistic particle. For a non-relativistic particle, this means one moving slowly by comparison with the speed of light, and it's just F equals ma. Force is equal to mass times acceleration, but now I have to tell you what the force is. The force is given in terms of the, first of all, the charge of the particle, called Q. Then there's a term proportional to the electric field. The electric field is a vector. That makes sense. Acceleration is a vector. And a magnetic term, which is velocity dependent. Depends on the velocity. Again, it's proportional to the electric charge. It contains the velocity vector cross the magnetic field. Depending on your choice of units, some familiar units put a c down here where c is the speed of light. I'm going to leave it out. You will find in some choices of units, in fact in a lot of choices of units, the speed of light is included down here, but this doesn't matter. You can either absorb the speed of light into a new definition of the charge or a new definition of the magnetic field, or you can remember that it's always v divided by the speed of light. When I write v, you can think to yourself, he really means v divided by the speed of light. Either way, the main structure of the equation is mass times acceleration is equal to an electric field term plus a magnetic field term. The magnetic field term has the property that the force depends on the velocity, but unlike a friction force, the force is perpendicular to the velocity. Cross products are perpendicular to the constituent vectors which make them up. So, and in fact, what that means is that if a particle is moving, the magnetic force does not accelerate it along the trajectory, it accelerates it perpendicular to the trajectory, and for that reason, it doesn't change the speed of the particle. Not changing the speed of the particle means that it doesn't change the kinetic energy. Magnetic fields do no work. That's the catch phrase. All right, so this is one form. As I said, I will mainly be interested in magnetic fields or motion in the plane of the blackboard, the whiteboard, where the magnetic field is perpendicular to the plane. The velocity, of course, is in the plane. So the velocity is in the plane. The magnetic field is perpendicular. The cross product of V cross B is also in the plane. It's perpendicular to B. If B is perpendicular to the plane, the force lies in the plane. So the whole motion takes place in the plane, or can be constrained to take place in the plane. And if the electric field also lies in the plane, that just gives another contribution to the acceleration in the plane itself. All right, so this is our setup. Now, let's go to the principle of least action. Oh, let me write down one other equation, which doesn't come in any useful way into the equation of motion in this form, but it is necessary to go either to make the step from equation of motion to any of these other formulations. You need another idea. You need the idea of the vector potential. All right. The vector potential. The vector potential is just defined by saying the magnetic field is equal to the curl of some vector that's called the vector potential. Now, there's something special about vectors which are curls of other vectors. Anybody know what it is? They have zero divergence. We talked about what a divergence is, but basically it's the spread of the vector field away from a point. Anything which is a curl has zero divergence. The magnetic field has zero divergence. What about an electric field? Does an electric field have zero divergence? If we write the divergence of the electric field, del dot E, what's on the right-hand side? The charge density. The charge density. What is it telling us that del dot B is equal to 0? Yes, it's telling us that there's no analog in nature of electric charge which creates sources of the magnetic field. No point magnetic sources which create magnetic field. Now, is it true that there really are no magnetic monopoles? Probably not. But nobody's ever discovered one, so until somebody discovers one, we can at least assume that for the purpose of the physics that we normally do, that there are no magnetic charges and the curl of the divergence of the magnetic field is 0. Any field whose divergence is 0 can always be expressed as the curl of something else, but not in a unique way. Not in a unique way. We'll come back to that non-uniqueness. There's a non-uniqueness in the vector potential here, that the vector potential can be changed without changing the magnetic field. The equations of motion only depend on the magnetic field. We could write that the magnetic field is the curl of the vector potential, but the equations are such that changing the vector potential, keeping the magnetic field the same, doesn't change the motion of the particle. That's called gauge invariance. We will come back to gauge invariance. In fact, we'll probably come back to it tonight. But for the moment, just keep in mind that this construction of a vector potential is ambiguous. I'll give you some examples as we go along. What about the electric field? How do we usually represent that? The electric field is just a more ordinary non-velocity dependent force. It's very much like the ordinary forces that we've studied up till now. It doesn't depend on velocity. It does depend on position. It's also conservative. Conservative means that it respects the conservation of energy. And what do we know about conservative forces? We know that they're generated from potential energy functions. From potential energy functions, force is equal to minus the gradient of a potential energy function. To write it in terms of components, It's the equation that we've written. The ith component of the force is minus the derivative with respect to xi of a potential energy function. Now, in electricity and magnetism, it's normal. Oh, all right. First of all, the electric force has this, this particular behavior. And to ensure it, what one writes is that the electric field is equal to minus the gradient of a quantity called V. V is essentially the potential energy, but not quite. What's it missing? Well, we have mass times acceleration is equal to charge times E. So E is not quite force. Charge times E is force. And therefore, potential energy is charge times V. That's all. The V, what does V stand for? Volts. It's measured in volts. And a volt is an energy per unit charge, is what it is. That's all a volt is it's an energy per unit charge. And this is a convention to some extent that we, instead of writing U, we write V, but then multiply it by Q to find the potential energy of a charge. But it also tells us that all things being equal, the force and the potential energy on a charge is proportional to the charge. Double the charge, you double the potential energy, and so forth. Okay, so we could rewrite these equations here in terms of the potential V, sometimes just called the electric potential, and the vector potential A by just plugging in to here and here. Let's come next to the principle of least action. The only known formula for an action which gives rise to this equation requires you to use the vector potential. You can't get away with it. Nobody knows, and in fact you can prove, that you can't write a principle of least action which deals directly with the magnetic field. You have to use the vector potential. Well, that's a little bit odd, because at the end of the day, the behavior of a particle doesn't depend on the vector potential. It depends on the magnetic field. You can change the vector potential without changing the magnetic field, and the motion of the particle doesn't depend on the vector potential. But nevertheless, to write the principle of least action, you must introduce the vector potential. Here it is. The action for a particle is, as always, is an integral. It has the usual 1/2 mv squared, the kinetic energy, 1/2 m, let's write it out explicitly, x dot squared plus y dot squared. I'm leaving out the z component of the motion because, as I said, let's concentrate on 2 dimensions. If we wanted to put the 3rd dimension in, we would. Mx dot squared, or just mv squared. It then has the good old potential energy, which would just be minus u. For an ordinary potential energy, we would write minus u of x and y. Now we write minus charge times v of x and y. And we integrate this dt. What else would we integrate it with? dt. But then that does not capture the physics of the magnetic field. We have to add plus the integral, again the charge, the vector potential. Let's write it in components first. A sub I dx sub I. We take the path and we break it up into little infinitesimal segments. Each segment is a dx and a dy. We call the combination dx and dy, we call it dx sub I. And we take the component of the vector potential, multiply it by the corresponding component of dx, and integrate it. We don't need any dt in here, we have a dx. So that's just along the trajectory, in each little interval there, we can call it dx dot A. If we think of dx as a little vector and A as a vector, then what appears here is A dot dx. Okay. So this is also an integral along the trajectory. From the beginning, I won't bother putting in the boundaries, the endpoints of the integration. It's from the beginning of the trajectory to the end of the trajectory, and that is the action for a particle in an electromagnetic field. Now, let me take, just to show you some of the symmetry of this formula, let me take this term and put it over here and write it as minus q v dt. Let's remove it from here. This is kind of interesting. Q comes out. Q goes along with all of the terms. What do we have here? We have for each direction of space, we have an a sub I times a dx sub I, and then for the time component, we have a v times dt. It's as if we plotted the motion in space-time. Now, we're not talking about relativity for the moment, but you can see that what's being set up here is going to be particularly simple when we think about the special theory of relativity, where x and t form space-time. But let's put in t here, x and y, and imagine a trajectory. We now break up the trajectory into little bits, and now what we have from the electromagnetic field is a term a sub I dx sub I minus v dt. It's almost as if, not almost as if, it is as if v was the fourth component of a vector potential, and that this is a combination that involves all four directions of space, all four directions of space and time dotted into a three-dimensional vector potential and its fourth component. Now, if you're not familiar with special relativity, don't worry about it. Right now, this is the form that the action takes. This a dx looks a little bit unfamiliar. Up till now, our action has involved the integral of a Lagrangian, and a Lagrangian is a function of velocities and positions. A is a function of position. A is a vector field in space. It depends on position. All three components of it depend on position. V also depends on position in general. A could also depend on time, and so could V, but it does not depend on the velocities. So this is something which depends on position, but it has this odd form of being multiplied by dx sub I. Well, to get it to look more ordinary, just divide by dt and multiply by dt. We can also divide by dt over here. And now we see that the Lagrangian for the particle in the electromagnetic field has the usual form. Yeah, we could write this VI.
No, I don't mean that. I mean the V term.
Here.
Yeah.
No. V is a scalar.
So basically we have A dot dx, and that's a sum.
Oh yes, oh yes. A dot dx is a sum.
And the V part is not sum.
No, that's right. But we're calling we're going to wind up calling, as usual, two things by the same symbol. There's velocity and there's potential. I'll try to use, if I ever, here it is right here. Let's be careful. Let's call this small v for velocity. A sub I dx sub I dt can also be written as the dot product of the vector potential with the velocity. All right, so let's do that. Let's just call this A dot v. Sorry, A dot small v. And these are both vectors. So that's our Lagrangian. This is our principle of least action. The true trajectory minimizes the action. And it immediately tells us what the Lagrangian is. To get the Lagrangian, all we have to do is erase the integration signs and the Lagrangian is plus q times a dot v, a dot little v, minus v of x. This is now on the wrong line. It should be next to Lagrangian here. We can go through the construction of the Hamiltonian. I won't do that now. It's a standard construction. Let's leave that for either later. Maybe we won't even need it very much altogether. But let's concentrate now on the gauge invariance. What kind of things can you do to the vector potential that don't change the magnetic field and therefore do not change the physics? Remember, the real basic differential equations here do not involve the vector potential. That means there's some sort of redundancy of the description, because we can change the vector potential without changing the physics. And we can also think of it as a kind of symmetry of the system where changing the vector potential in a certain way has no influence on the motion. It's a kind of symmetry. It's called gauge invariance, and here's the way it works. Let's take as a, let's just to understand it, let's focus on a particular component of del cross A. Let's say the z component. But all the other components work the same way. What is the z component of del cross A? It is derivative with respect to x, that means d by dx, of ay minus the derivative with respect to y of ax. That's its definition. All right. Now, supposing I add, I'll write it in vector notation and then just explicitly in components. Supposing I add to the vector potential something which is itself a gradient. I'm going to call it lambda, lambda of x. What is a gradient? A gradient simply means the ith component, we add to the ith component of A, we add derivative with respect to xi of lambda. Now, lambda can be anything. The point is that changing A in this way doesn't change the curl of A. Let's see why that is. Supposing I now recalculate the curl of A after having introduced this extra term here. For example, let's take the x and y component. A sub x will now have the new term d by dx of lambda, and a sub y will now have the new term d by dy of lambda. Lambda of x means lambda of x and y in general. Okay, x and y. Let's just leave it that way. Okay, what happens to the curl? The curl gets another piece. It gets a plus derivative with respect to x of the new term in ay. The new term in ay is d by dy of lambda. But then we have to correct this term, that's minus d by dy of the new term in ax. The new term in ax is derivative with respect to x of lambda. Well, these are exactly the same thing. d by dx, d by dy of lambda is exactly the same thing as d by dy, d by dx. The order of operations of derivatives is immaterial. And so by adding the gradient of a scalar to a vector, it does not change its curl. Another way to say it is the gradient of a scalar doesn't have a curl, is curl-free. So, by adding to the vector potential the gradient of a scalar, we change the vector potential, we change the Lagrangian. but we don't change the equation of motion. Right? I will remind you, it's somewhere in your notes, I worked out, well, maybe we should do it. Let's do it over again. Let's, just to keep the lecture self-contained. Let's work out the equation of motion, and starting with the Lagrangian, and see that it really does have the form. Incidentally, this equation up here has a name. The right-hand side is the Lorentz force law. Lorentz, L-O-R-E-N-T-Z, the same gentleman who first wrote down the Lorentz transformations. Okay, so this term is called the Lorentz force law. Let's check that this Lagrangian gives rise to Lorentz's equation of motion for the motion of a particle. We just do the usual thing. Let's just do the x component. We'll just do the x component. Let's not bother with the y component. We start with the x component, and we first calculate the canonical momentum conjugate to x. That's the derivative of the Lagrangian with respect to x dot. So p sub x is equal to the derivative of Lagrangian with respect to x dot. That's mx dot. Well, that's not surprising. That's just mv. Good old momentum. But then there's another term. The x dot also appears in a dot v. This is x dot times a sub x. So there's another term, q a sub x, and that's it. Q times a sub x. So we see something odd, that the canonical momentum is equal to the thing we usually call momentum, mv, plus an extra term which depends on the vector potential. But this is strange, because the extra term is itself not gauge invariant. It depends on the vector potential. If I change the vector potential by adding something to it, I will change the momentum. Well, that's okay. We follow the mathematics. If the mathematics tells us to do it, we do it. The canonical momentum of a point particle in a magnetic field is not gauge invariant. It means it's not a thing you really measure. It depends on your choice of the vector. We're going to give some examples of different choices of vector potentials and see how the whole thing works. But this is the canonical momentum. Now, what's the equation of motion? The equation of motion is that the time derivative of this, the derivative of px with respect to t, is equal to the derivative. Now this is just Lagrange's equations. d by dl, let's write it down. Derivative of Lagrangian with respect to x dot d by dt, that's just derivative of p, is equal to partial of L with respect to x. Well, the left-hand side is just the time derivative of this. So we can write mx double dot, that's the first term of d by dt, dl dx dot. And then the second term is plus q times the time derivative of a sub x. I told you that a sub x was not a function of time. Does that mean that it doesn't depend on time? No. What it means is it doesn't depend explicitly on time. Here's the point. You may have a field in space which varies in space but does not vary in time. All right? It doesn't vary in time at all. It's just something, some spatially dependent thing. But if a particle moves through it, then by virtue of the motion of the particle from point to point, the field at the particle does change with time. Right? And to work out the change in time, we just write that this is equal to the derivative of a sub x with respect to x times the time derivative of x plus the derivative of a sub x with respect to y times the time derivative of y. All right? A sub x at the position of the particle changes because the particle is moving, and here's the time derivative of a. That's the left side. What about the right side? Equals. Now, what he had depends on x. Let's write this out. This is q a sub x times x dot plus a sub y times y dot minus v of x and y. Oh, there should be a q here. Yeah, q. All right, what depends on x? Ax depends on x in general, ay depends on x, and v depends on x. The x dots don't depend on x. Just ax and ay and v depend on x. So on the right-hand side, let's write down what we get. We get q times the derivative of a sub x with respect to x times x dot. What I'm writing is partial of L with respect to x. So we get one term by differentiating a sub x over here with respect to x, another term from differentiating a sub y with respect to x. Let's plus q derivative of a sub y with respect to x times what? Times y dot. That's the derivative of this term with respect to x. And then we get minus q dv by dx. First of all, q dv by dx. What is that? That's q times the electric field. So that's this term in Lorenz's force law. We can forget about it for now. That's in good shape. On the left-hand side, we have some terms, each of which involves the derivative of a with respect to x times some sort of x dot. On the right-hand side, we have similar things. Perhaps some of them cancel. Let's see what cancels. Both the left and the right, we have the ax sub x with respect to x times x dot. Here and here. So the whole right-hand side then, what do we have here? Sorry. We can now transpose this term over here to the right-hand side, and let's see what we have. We have, first of all, from here, q, then the ay by dx times y dot, and then from here we have minus dax by dy times y dot. The ay by dx minus the ax by dy, what is that? That's b sub z. So this is q times b sub z times y dot. That's exactly this term here. It has a velocity, it has a magnetic field, and if we're interested in the x component of v cross b, then it has bz and y component of velocity. So that's this. So indeed, we do reproduce the Lorentz equation of motion, but even more than that, we see that the vector potential only appears in the form of the magnetic field. Despite the fact that we had to use it to write down the Lagrangian, the vector potential appears in a gauge invariant way. In other words, what appears here, the B field, does not change when you make a gauge transformation. So that's one of the oddities of physics, that it requires you quite often to introduce some redundant descriptions of things. It's not that you have to introduce a redundant description of things. You could have worked just with this. But in order to make the equations look like principle of least action, Lagrangians, Hamiltonians, and so forth, there are times when you have to introduce redundant descriptions of things, and those redundant descriptions are called gauge invariances. the transformations which correspond to these redundancies, the changes that you make that are really no changes at all in the underlying physics, those are typically called gauge transformations. So whenever you hear about gauge invariance, one is always talking about some kind of redundancy that's necessary to work out the canonical formulation of a theory, but where the redundancy doesn't enter into the actual motion of a system. Okay, so there we are. We have the Lagrangian. We have this. Now I want to give you some explicit examples of vector potentials. In particular, I want to concentrate on the problem of a uniform magnetic field, one which doesn't vary from place to place. That's the simplest situation. Magnetic field pointing into the blackboard, which has no variation, just a uniform, constant magnetic field. How do we construct one from a vector potential? We want Bz to be independent of position. So Bz is equal to derivative with respect to x of Ay plus minus derivative with respect to y of Ax. I'll give you two examples of vector potentials which do the job. We want Bz to be a constant. Let's say a constant, let's take B, let's assume that B is into the blackboard. In other words, it is positive, and its magnitude, I'll just call little b, the magnitude of the magnetic field. All right, then we can take A sub, here's an example. Take Ay equal to the number B times x, and Ax equals 0. In that case, the derivative with respect to x of Ay is just b. The x goes away when we take the derivative. On the other hand, Ax is equal to 0, and this doesn't change the answer. So this is one possible choice of vector potential which will give rise to the uniform magnetic field. Here's another one. Ay equals 0, and Ax, anybody want to guess? Minus b times y. Just check it. This time the x of Ay is equal to 0, but the y of dAx is equal to minus b, and gives you the same answer. Here, I'll give you another example. It has to be minus because there's a minus here, yeah. If we want to get the same answer, yeah. Here's another example. All giving the same magnetic field. Ay equals b over 2x. Ax equals minus b over 2y. Also will give the same answer. These different vector potentials are related by gauge transformations. It's not too hard to work out that there's some scalar, I won't write it down, there's some scalar that takes you from one to the other by taking its gradient. All right, so these are three different, and there's an infinite number of other ones, an infinite number of other formulations for the vector potential which give exactly the same magnetic field. One can use any one of them. It doesn't matter, since the net final equations of motion don't depend on the vector potential, they only depend on the magnetic field. Let's take these two examples. Let's forget this one here and concentrate on these two. Let me rewrite it. Ax equals by, Ay equals 0, and the other possibility is Ay equals 0, Ax is equal to, Ax is equal to 0, Ay is equal to minus b times x. In the lingo, these would be two different gauges. Two different gauges giving rise to the same field. Okay, let's see what we learn from conservation laws. Let's start with this gauge over here. Okay, let's forget the second gauge. Let's start with a gauge in which AX is equal to BY and AY is equal to 0. Let me rewrite the Lagrangian in detail now. And I'll tell you what, for simplicity for the moment, let's forget the electric field. We'll come back to the influence of the electric field in a little while. Okay, so A times V means now AX times X dot. I've set AY equal to 0 in this first choice of gauge. Okay. And furthermore, AX is equal to B times Y. So that's my Lagrangian. And now let's calculate the canonical momenta conjugate to X and to Y. Let's start with Px. Px is the derivative of the Lagrangian with respect to X dot. That's Mx dot plus QBY. Is this conserved or isn't it conserved? Well, let's write down the other one. Py is equal to My dot plus nothing. Which one do you think, if any, are conserved? All right, we'll take a vote. Is this conserved? Is this conserved? Are any of them conserved? Yes? No? Good. What? Yeah. Okay, but still, are any of them conserved? That's one possible answer. Anybody say yes? Oh, come on, I want to embarrass you. Okay. This one is conserved. Why is it conserved? This is the X component of momentum. And notice the Lagrangian doesn't depend on X. It depends on X dot, but X dot is not X. And it depends on Y. If I make a transformation, X goes to X plus epsilon. The X component of the velocity doesn't change. I've just translated the system a little bit in the X direction. That doesn't change X dot. It doesn't change Y dot. It doesn't change X dot over here. And it doesn't change Y. Why? Because I haven't changed Y. That's why. Huh? That means that the X component of momentum is conserved. There's a symmetry. X goes to X plus a constant. What about Y goes to Y plus a constant? This term changes. If you shift Y a little bit, this term changes. So the Y component of momentum is not conserved. All right, let's forget it since it's not conserved for the moment. What we've learned is that in this gauge, this quantity is conserved. Well, I don't need to say in this gauge. I can just say Mx dot plus QBY is conserved. For example, if it starts out being 0, let's take that case. Suppose it starts out being 0, then it will stay equal to 0. Let's take that case for simplicity. If it starts out 0, it stays 0. If it's not 0, it'll stay whatever it is. Okay? And we'll understand in a little while what that means. Okay, that tells me, that immediately solves for me and tells me that X dot, the X component of velocity, is minus QB over M times Y. That's what I learned from conservation laws. It's very odd. First of all, it's odd because the X component of momentum is not what you might have thought, namely just X dot, Mx dot. And second of all, in the particular gauge that we're writing, since there's an X translation invariance, we can immediately conclude that the X component of momentum is conserved, and that tells us if it starts 0, it stays 0. Later on, we'll worry about what if it's not 0. Okay, now let's go to the other gauge. Oh, and incidentally, this equation here, that x dot, this doesn't have anything to do, this is completely gauge invariant. It just tells us that the velocity, the x component of velocity, is proportional to y. Let's find out another piece of information by working out the theory in the other gauge. In the other gauge, the Lagrangian becomes minus QB x times y dot. The y component of momentum, which is now the one I'm going to be interested in, Py, is my dot minus qbx. In this gauge, Py is conserved. Oops, sorry. Y dot, yeah. In this gauge, Py is conserved. Why? Because the Lagrangian doesn't depend on y. Seems to me I said that before. Do I have a... Lagrangian doesn't depend on y, so Py is conserved. Okay. A shift of y doesn't change the Lagrangian. In this gauge, a shift of x changes the Lagrangian. But a shift in y doesn't change the Lagrangian. And so this quantity here is also conserved in the motion of a charged particle. For example, if it starts 0, it will stay 0, in which case y dot is equal to, this time it's plus, qb over m times x. I haven't had to solve any equations. All I did was write down the conservation laws, and I found out that the x component of velocity is proportional to minus y, and the y component of velocity is proportional to x. That should ring a bell to some of you, maybe not to all, but we'll work it out. I'll ring your bell for you. What kind of motion is this? That's circular motion. So let's prove that it's circular motion. And see what we can find out about the circular motion. Let's consider a particle moving in a circle about the origin for simplicity. What is its equation? Well, let's call this angle theta. Let's call its distance from the origin r. Then x is equal to r times cosine of theta. But if we're going to allow theta to evolve and swing around here with an angular velocity omega, we can write that this is equal to r cosine of omega t, and y is equal to r sine omega t. This is uniform motion with an angular velocity omega. Number of radians per second is omega. Let's check that this solves this equation here. So what is x dot? X dot is just differentiating this with respect to time. That's equal to r omega, and then the derivative of cosine is minus sine omega t, and y dot is equal to r omega cosine omega t. X dot is supposed to be minus something times y. X dot is minus something times y, and y dot is supposed to be that same something times x. Y dot is that same something times x. In order to find out what omega is, we just have to match these equations. So here we have x dot is equal to minus qb over m times y. Here we have that x dot is minus omega times y. X dot is minus omega times y. The r's cancel out. All right? So I can write just from this here that x dot is equal to minus omega times y, and also a similar equation for y dot. Well, if I compare that with this equation here, I immediately find that omega the angular frequency, it's called the cyclotron frequency, is equal to minus QB over M. Yes. And it's omega. What am I writing Q? Omega. Omega is QB over M, the charge of the particle divided by its mass. Notice that combination, ratio of charge to mass, times the magnitude of the magnetic field. That's the angular frequency. The larger the charge, the larger the angular frequency. The larger the mass, the slower the angular frequency. This combination, Q over M, was what made it hard at about the turn of the 20th century to determine the charge and mass of the electron, because it always comes into most things in the ratio Q over M. And so measurements of the trajectory of electrons and so forth in magnetic fields yield the ratio of Q to M, but it doesn't give Q and M separately. Something else had to be done to do that. Okay. Now, the whole thing may strike you as odd that we have this redundancy of description. We can shift the vector potential, change the whole formalism, but nevertheless extract out interesting and useful information from the conservation laws. In fact, I used two different gauges to get two different pieces of conservation laws. What happens if I did not require px, let's write this correctly. I think we had px is equal to mx dot plus qby, but that was in gauge number 1. Gauge number 1 means this one over here. And an entirely different gauge number 2, we had py equals my dot minus qbx, gauge 2. Because the real motion doesn't depend on the gauge, I could use gauge 1 to calculate what x does. I could use gauge 2 to calculate what y does. So it's an odd kind of logic. The circular motion about the origin here corresponded to both this px and this py equal to 0. If I set this equal to 0, that's setting my equal to qbx. What if I have a circular motion, since after all, the magnetic field is completely uniform. One place is exactly the same as another. I should be able to consider a circular motion moving around some other point. Let's consider that, and then calculate whether these quantities are still conserved. To do that, all we have to do is add an x naught here and a y naught here. X naught and y naught are just the center positions, the central coordinates of the circle, x naught and y naught. I've shifted the circle by amount x naught and y naught. No, you're absolutely right. It's a good thing you caught me before I did it. Here, plus x naught plus y naught. Doesn't change x dot and y dot at all. Okay, let's calculate what mx dot plus qby is. Okay, mx dot is m r omega minus r omega sine omega t. Plus qby. What is y? R sine omega t plus y naught, right? That's px. Now, assuming again that omega is related to q and b, where is it? Where's the connection between, here it is, qb over m, then these cancel each other. qb over m is omega, so these again cancel each other, and we simply find that px is conserved. It's just equal to y naught, the central position of the circular motion. The central position of the circular motion, of course, does not change with time because we're talking about a circle moving about a fixed central position. Likewise, this py over here will be I don't quite have that right, do I? It's qb times y naught. qb times y naught. The qb comes from this qb over here. And the py is minus qb x naught. So you see what the physical meaning of the momenta is. It's something entirely unexpected. The two momenta in the two gauges, the x component and the y component, which are conserved quantities, simply correspond to the coordinate locations of the circle about which the particle is revolving. And what the conservation tells you is that the central location of the circle doesn't move, just stays there. Entirely unexpected way to think about momentum conservation, but this is exactly the way a charged particle moves in a magnetic field. So you have to trust Lagrange and Hamilton and so forth that they knew what they were doing, and you have to trust gauge invariance, but the mathematics gives you the right answer. And in fact gives you the right answer in probably what's the easiest possible way, just to use the conservation laws. Okay, let's stop for questions for the moment. Yeah. What's that? This one? You mean it's units? Yeah. I don't know. What's the units of Q? Do you know? Yeah, exactly. Yeah. If you choose consistent units, the units will be consistent. All right. So let's go one step further and do one other thing. Let's put back the electric field. Let's put back the electric field. If I put back the electric field, then, and let's take this px over here. Let's put an electric field in the x direction. All right? Then it will not be the case anymore that px will be conserved. Why? If there's an electric field in the x direction, let's go back. Okay. Yeah, let's put an electric field in the x direction. That means a potential which looks like a potential which looks like some electric field, magnitude of the electric field times x, times minus x, I believe, if I want the electric field to point in the x direction. Here, E is just the magnitude of the electric field. And remember, the derivative of v sub x, the derivative of v with respect to x is E sub x. Derivative of v with respect to y, in this case, would be 0. So the derivative of v with respect to x would just be, sorry, minus sign here, would be E equals 0. Okay, how does that affect these equations? Well, it doesn't affect this equation. The canonical momentum conjugate to x is still, it affects this equation here. Puts in minus v which is plus E times x, QE times x. QE times x now is the electric field force, or is the electric field energy, if you like. Now, the canonical momentum in this gauge is still just p sub x. It's just mx dot plus qby. It hasn't changed because this doesn't depend on the velocity, but it's no longer conserved. Its time derivative is equal to the x derivative of this. Why? That's Lagrange's equations. Lagrange's equations, d by dt of partial of L with respect to x dot, but that's just p sub x, is equal to dl by dx. And now we do have an x dependence. We just have QE. Okay, so now instead of having a conserved quantity, we have the new equation that, let's write it out. The time derivative of px is mx double dot plus q b y dot. I've taken the time derivative of p sub x, and that's equal to q times e. What about the other equation? What about the equation for p sub y in the other gauge? That's unchanged because I haven't put any force in the y direction. So in the y direction, there's been no change. M y double dot plus or minus q b x dot is still equal to 0. All right, now I want to look for a particular kind of solution of the equations. Just for simplicity, only for simplicity. I want to look for a solution with no acceleration. Let's just look for a solution with no acceleration. That means the particle is somehow moving with uniform velocity. Ordinary Newton's equations, of course, have such solutions, and any velocity is a possible velocity. Well, that's not true anymore. Let's look for a solution of the equations with no acceleration. That means that the velocity has to be constant, but it can't be any constant. Let's throw these terms away and see what we get. From here, we get that x dot has to be equal to 0. So if we plot x and y, x dot has to be equal to 0. The particle doesn't move to the left or the right, but from here, we see that y dot is equal, the q's cancel. Let's see, y dot is equal to E over B. Is that right? Is the ratio of the electric to the magnetic field. So, how does the particle move? It moves with a constant velocity. Oh, this is constant. Notice that y dot is constant, and therefore we check. There really is no acceleration. I was correct in looking for a solution with no acceleration. But what I find is a very special kind of velocity, namely a velocity in the x direction with uniform motion equal to the ratio of the electric to the magnetic field. It can be anywhere. It can move over here, it can move over here, but it moves with a very specific velocity in the y direction. Now that's kind of interesting because I put the force in the x direction. I put the electric field in the x direction. E was in this direction, and it causes the particle to move along the y direction. A bit of a surprise. That's called the Hall effect. If you have a magnetic field, first of all, if you have a magnetic field and no electric field, then first question, is there any solution with no acceleration? Motion in a circle has acceleration. But nevertheless, there are solutions with no acceleration, namely a circle of 0 radius where the particle just sits still. That is a solution of the Lorentz force law. No acceleration, no velocity. We have no electric field now, no velocity, no acceleration. That's a solution. But when we turn on the electric field in the x direction, the particle moves off along the y-axis. That's called the Hall effect. In fact, if you take a distribution of charge in the plane and you impose a magnetic field into the blackboard, and you don't stir up the particles to give them any special kinetic energy, they will just sit there. But then if you turn on an electric field in the x direction, the whole flow of charge will be along the y-axis. And the velocity will not depend on the charge, but it will depend on the ratio of electric to magnetic field. So that's called the Hall effect. And
They have something in hard disk drives called a Hall effect motor.
a Hall effect what?
Motor. And they use it to spin up the drive.
Spin up the what?
Spin up the drive. Hard drive.
Oh, is that right?
Yeah.
I don't know about it.
It's one of the kind of expensive components of the mechanism.
I see.
Because it takes a big magnet.
It's not in ordinary computers, is it?
Yeah.
It is? Oh.
In hard disk drive. Winchester disk.
No. Okay. Why it spins up anything, I don't really know, but I can guess why it might, but let's not guess. Okay, that's the Hall effect. It's very similar, and the mathematics is very close, but I won't do it, to the gyroscope effect. The gyroscope effect is if you have a spinning top spinning along the x-axis, and it's in a gravitational field pulling it down, it doesn't go down, it processes in the perpendicular direction. Same mathematics. Very similar mathematics. Okay, that's the motion of a charged particle as described at least in these three ways. I will write down for you what the, I won't, I'll assign it as a problem. I think it's one that I did in class, but to work out the Hamiltonian of the charged particle and work out Hamilton's equations and see that you get the same answers, of course. All right, so we've been through some good stuff: electric particles, magnetic particles, gauge invariance. Now I want to come to another form of mechanics. It's really very closely related to Hamilton's form. It's a kind of abstraction out of Hamilton's forms of mechanics. It's called the form in terms of Poisson brackets. Now, this is highly abstract. It is not something that I would bother teaching you if it were not for the fact that it's so centrally related to quantum mechanics. It is much easier to understand the quantum mechanical origin of this than it is to understand the classical mechanical origin of it. One usually thinks that classical mechanics is something much easier to understand than quantum mechanics. Well, at some point, it becomes quite clear that the classical mechanics is really some overly complicated way of describing how the motion of wave packets behaves in quantum mechanics. And in quantum mechanics, the whole idea of Poisson brackets is really very much easier. But nevertheless, since we've come this way without quantum mechanics, and since it is considered a part of classical mechanics, I'm going to teach you about Poisson brackets. I think we've already talked about it a little bit, but there's an entirely there's a entire formulation of quantum mechanics, classical mechanics, which is based on Poisson brackets. Poisson brackets and canonical transformations. We will not get the canonical transformations tonight, but we will get the Poisson brackets right now. Let's begin with Hamilton's equations of motion. Now, I know I did this before, but it never hurts to do a thing again. Now, I always forget where the sign goes. P squared over 2m dv, yeah, that's equal to q sub I dot. I'm now using p and q rather than p and x. And dh by dq sub I is equal to minus p sub I dot. These are the two Hamilton equations of motion, one for each component I, or rather two for each component I. Double as many equations as the Lagrange form, but the equations are first order instead of second order. They contain only first time derivatives. All right, let's take some function of p and q, any function, p squared plus q squared, or any function of momenta and velocities. Some things that we might measure. I'm having a hard time thinking of something that would be interesting to measure, but all the interesting quantities that one would do experiments on in a classical mechanical situation are functions of velocity and position, or equivalently functions of momentum and velocity and position. So let's take some arbitrary function a of all of the p's and all of the q's. All right, so here's our phase space, and we have some function which varies from place to place in the phase space. Well-defined function. When the fluid moves through the phase space, the value of this function changes with time. Not because the function changes with time, but because the point in the fluid is moving through the fluid and changing with time. How does A vary with time along a trajectory? Well, that's not too hard to figure out. Let's just differentiate it. A dot, this is the time derivative of A along the trajectory, assuming that A has no explicit time dependence. Well, that's going to be the derivative of A with respect to P sub I, times P sub I dot. And when I write a thing like this, you can assume that I mean sum over I. I'm not going to explicitly write all the summation signs, plus the derivative of A with respect to Q sub I times Q sub I dot. But now let's use Hamilton's equations. This becomes partial of A with respect to P sub I times, looks like there's a minus sign here. I wanted to start with the plus sign, so let's start with the plus sign. The A by dq sub I and q sub I dot is dh by dp sub I. And then we have dA by dp sub I times p sub I dot. But p sub I dot, first of all, has a minus sign, and then it has dh by dq sub I. This combination, given two functions, in this case A and h, but they could be any two functions of positions and momenta, there's an object called the Poisson bracket, and this is it. So let's write it generally. For a general pair of functions, let's call them A and B now. Then, by definition, the Poisson bracket of A and B is first of all represented by an A and a B with a comma in between, sandwiched between two squiggly brackets like that. That's called the Poisson bracket. And it's by definition summation. I'll now write the summation sign when writing definitions, I'll just to be very clear. Summation over I derivative of A with respect to Q sub I, derivative of B with respect to P sub I, minus derivative of A with respect to P sub I, derivative of B with respect to Q sub I. The Poisson bracket of A with B is not quite the same thing as the Poisson bracket of B with A. What's the relationship? Not quite. This is not true. Minus. There's a minus sign. If I interchange the A and B, these two terms, well, if I interchange the A and B, they switch, and this would be minus. So the Poisson bracket is an anti-symmetric expression involving any two functions. That's number one. So you have to remember which one you wrote down first. I have to keep track of it. But this is it. That's its definition. What did we prove a moment ago? We proved that the time derivative, d by dt along a trajectory of any function of A and P and Q is equal, now it's either plus or minus, plus the Poisson bracket of A with the Hamiltonian. So this, of course, includes the two Hamilton equations. For example, supposing we chose for A, what's the simplest thing we could choose for A? Either P or Q. I'm going to stop writing sub I. Let's just do this for one P and one Q, but it's the same for many of them, just because I don't feel like writing subscripts all over the place. Let's concentrate on one P and one Q, but nothing I do is special to that case. You can figure out where to put the summation signs and the indices. What's the simplest thing that A could be? P? Well, P is pretty simple. What else? Anything simpler? How about zero is very simple. 1 is pretty simple. Just the function 1. The function which is everywhere is the same on the entire phase space, doesn't vary on the phase space. What's the time derivative of the function 1 as the particle moves through the phase space? 0, because 1 is just 1 everywhere. Let's just check that. Supposing I plug in, for A, I plug in just 1. Well, the derivative of 1 with respect to either a P or a Q is 0. So quite obviously, the Poisson bracket of 1 with anything is 0. Okay? So the function 1 does not change. Let me make use now of your brilliant suggestions of a moment ago. Let's let A just be P and see what we get. All right, the left-hand side will just be dP by dt. The right-hand side will be dP by dQ dH by dP minus dP by dP dH by dQ. I have just substituted in for A, P. dH by dQ, sorry, dP by dQ, dH by dP, minus dP by dP, dH by dQ. Now, dP by dQ is 0. P and Q are independent variables, and the derivative of one independent variable with respect to another is just plain 0. So this is 0. What about dP by dP? That's just 1, and so we find dP by dt is just dH by dQ, one of Hamilton's equations. The other Hamilton equation is dQ by dt is equal to, now we substitute in dQ by dQ, dH by dP. And now we're going to have another term where we'll have dQ by dP, but that's 0. dQ by dP is 0. dQ by dQ is 1. So the other Hamilton equation is also of the form that the time derivative of an arbitrary function of P and Q is, in fact, equal to the Poisson bracket of the function with the Hamiltonian. So we're sort of reducing now the physics, all of classical physics, to a kind of algebraic structure involving Poisson brackets. Let me tell you a few properties that Poisson brackets have. They're actually sufficient to recover any Poisson bracket that you might be interested in. I'm just going to write down some properties. First of all, we've already encountered one property. A with B is minus B with A. You can think of this as a kind of axiomatization of mechanics based on Poisson brackets. Why is it interesting to do so? It isn't until you come to quantum mechanics, but it is very, very centrally, well, it may be interesting, but it really achieved its full glory, shall we say, when it was realized that how closely it is connected to the algebraic structure of quantum mechanics. A with B, Poisson bracket of A with B is minus the Poisson bracket of B with A. All right, how about the Poisson bracket of P with P? Now, we could write, I'm going to do P with P, but then I'll tell you what the answer is if there are any number of variables. What is P with P? Well, that's equal to partial of P with respect to P, partial of Q with respect to Q. Partial of P with respect to Q, partial of Q with respect to P. Yeah, you're right. Good. I don't even need to do it. The Poisson bracket of P with P is equal to minus the Poisson bracket of P with P from the above rule here. But anything which is equal to its own negative is 0. So Poisson bracket of P with P is equal to the Poisson bracket of Q with Q and is equal to 0. Now, we can go a little bit further. If we have a system of n coordinates, then we can take the Poisson bracket of 1p with another one, I with j. We'll still get 0. It's easy to prove. And we'll also get 0 for the q's. You can see there's a symmetry, well, not an exact symmetry, but some symmetrical relationships between p's and q's. They're on the same footing. How about p with q? Or let's go to q with p. Poisson bracket of q with p. That's equal to partial of q with respect to q, partial of p with respect to p, minus partial of q with respect to p, partial of p with respect to q. Well, the derivative of a q with a p or a p with a q is 0. So this is 0. The derivative of a q with a q or a p with a p is 1. And so the Poisson bracket of q with p is just 1. More generally, if I have q sub I and p sub j, then that's 0 if I is not equal to j. For example, if we take the Poisson bracket of the x coordinate with the y momentum, that's 0. So this is 0 if I is not equal to j, and it's 1 if I is equal to j. The symbol for that is the Kronecker delta symbol ij. Delta ij. Delta ij is by definition 0 if I equals j, not equal to j, excuse me, 1 if I equals j. Now notice that there is a little asymmetry. Q with P is minus P with Q. So if I were to put P with Q, I would get minus 1 instead of 1. So you have to remember, if Q is first and P is second, then not the commutator, the Poisson bracket is 1. But otherwise, there's a great deal of symmetry. In fact, the general structure of classical mechanics is that whenever you interchange Q and P's, there's always a minus sign. It's called the symplectic structure of classical mechanics. Okay. All right, some other rules. Here's something. How about the Poisson bracket of Q sub I? Well, I'll do it without indices, and then I'll tell you the general answer. The Poisson bracket of Q with any function of Q and P. Let's do P. P with any function of Q and P. Taking the Poisson bracket of a function with respect to P does something to that function. Let's see what it does. It gives you, first of all, dP by dQ, dF by dP, minus dP by dQ, dF, sorry, dP by dQ, dF by dP, minus, right, dP by dQ, dF by dP, that's right. dP, thank you. dF by dQ. Now, the first term is 0. dP by dQ is 0. The second term, dP by dP is 1, and so it just gives minus dF by dQ. In other words, rule, taking the Poisson bracket of an arbitrary function with respect to P is the same as taking its derivative with respect to Q, with the minus sign. If we wanted to do this with many variables, it would be the Poisson bracket of a function with P sub I gives you the derivative of the function with respect to Q sub I. So taking Poisson brackets with P's and Q's is basically the act of taking the derivative with respect to P and Q. Likewise, is equal to plus dF by dP sub I. So taking the Poisson bracket with a Q differentiates with respect to P. Taking the Poisson bracket with P differentiates with respect to Q, but you have to keep track of the minus signs. So actually, I think there's one more ingredient that you need to add in that would allow you to have a full algebra of Poisson brackets that could be used to axiomatize classical mechanics. I don't particularly like axiomatizing anything, but knowing these rules here is not quite enough to tell you what the Poisson bracket, just knowing these rules, without knowing, supposing nobody told you what a Poisson bracket was. They told you that Poisson brackets satisfy these relationships here. No, I'll tell you in a minute. Yeah, so something like that. Yeah, there is a linearity. Yeah, I'll write that down in a minute. They told you there's such things called Poisson brackets. They told you a little bit about the Poisson brackets, these things here, and then also told you that mechanics can be summarized by saying that the time derivative of anything is the Poisson bracket of that thing with h. How much do you need to know about Poisson brackets that you could start operating and completely forget where everything else came from? Well, you need to know, I think whoever said linearity, I think you do need that. All right, so here's the linearity. It hadn't even occurred to me, but yes. A plus B. All right, linearity means the following. It means that if you take any number times A and take its Poisson bracket with respect to B, it's just the same as multiplying the Poisson bracket by alpha. So that means if you multiplied A by 2, its Poisson brackets with everything would just be twice as big. No surprise there. Another thing, if you take the Poisson bracket of A plus C with B, that just gives you the Poisson bracket of A with B. You can check these things now. Check it from the definition. A with B plus the Poisson bracket of C with B. These two things together are called linearity. The linearity of the Poisson bracket with respect to one of the entries. If you double it, you double the Poisson bracket. If you add two things together and take that Poisson bracket with B, it gives you the sum of the two Poisson brackets. That's almost enough to determine the Poisson bracket of anything with anything else, any function of P and Q with any other function of P and Q. There is one more element. What happens if I take A times B, times now, not plus, A times B with the Poisson, or with C? Well, let's work it out and then abstract from what I work out the general answer. What is this? This is equal to derivative with respect to Q of AB times derivative with respect to P of C minus the derivative with respect to P of AB times the derivative of C with respect to Q. But now all we have to use is the product rule for derivatives. The product rule for derivatives says that this is A times the derivative of B with respect to Q times the derivative of C with respect to P. Now let me not finish this expression. I'll come back to the other half of it, but let me write it, let me combine it with A times the derivative of B with respect to P times derivative of C with respect to Q. That's the term that I get when I do the derivatives by pulling out A and differentiating B. Then there's another term where the derivative hits B and not A. That will be very similar, except A and B will be interchanged. So that will be B times the derivative of A with respect to Q, derivative of C with respect to P, minus B, derivative of A with respect to P, derivative of C with respect to Q. All right. If you summarize it all and put it all together, this piece here is just A times the Poisson bracket of B with C, A times the derivative times the Poisson bracket of B with C, and this one is just B times the Poisson bracket of A with C. All right, so the Poisson bracket of AB with C is A times the Poisson of B with C plus B times the Poisson of A with C. That, believe it or not, plus knowing a few fundamental Poisson brackets between P and Q, enables you to calculate any Poisson bracket. That's enough to get started. Calculate sums of things, P's plus Q's, calculate products, and eventually to calculate any function with any other function. I'll let you experiment around with that and see that you can calculate, or at least any functions that can be written as sums of products of functions of P and Q. Even infinite sums and products can be computed. So these basic rules, linearity, the product rule, the antisymmetry, and the fact that Poisson brackets of P with Q are 0 or 1 and so forth, those completely determine the entire family of Poisson brackets of anything with anything else. And if you then add that the rules of the game are that the time derivative, where did I put it? I think I erased it. That the time derivative of anything is Poisson bracket with a Hamiltonian. That is another formulation, a kind of axiomatic formulation of classical mechanics that, of course, is not independent of the others. It follows from the others, but it is another rather elegant. The French were great at this kind of super elegance. It wasn't the French who invented quantum mechanics, though. They were very, very good. What's that?
Like the great Frenchman Euler?
Yeah. Euler was a German. Germans were not as good at its super elegance. Yeah. This was before Bourbaki. Bourbaki didn't exist, of course. This was before Bourbaki, but there's no question the French were extremely good at finding these very elegant. Hamilton was another Frenchman, and Newton was another Frenchman, but the people who really, well, the person who really, the two people who really put Poisson brackets and all this stuff on the map were Heisenberg and Dirac, and not in the context of classical mechanics. So this will be next quarter, not this quarter.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.